Okay, we're back. This is free section video section 6.3, where we're dealing with partial fractions techniques of integration. All right. When trying to integrate fractions in which u-substitution did not work, now that's most important. You always try u-substitution first, and it did not work. Then the technique that we're going to be using to integrate fractions, very specialized fractions, is a technique called partial fractions. In other words, if you wanted to find the antiderivative of something like this, 17x minus 2 over x squared minus x minus 12. Okay, and here I've wrote it out. The integral of 17x minus 2 over x squared minus x minus 12. First things first, you've got to notice that u-substitution does not work. Okay, now, if I was going to do u-substitution on this thing, clearly you would let u equal to the denominator. U equals x squared minus x minus 12. Then I take du, the derivative, which is 2x minus 1 dx. And remember, with u-substitution, whatever you let u equal to, du has to be in the problem, up to a constant. Well, there's my u, but clearly my du is not in the problem. I've got 17x minus 2. And I need to have a 2x minus 1. That's not even anywhere close to the same thing. So u-substitution does not work. And notice something else. The denominator, the denominator, x squared minus x minus 12, actually factors. And it factors into x minus 4 times x plus 3. Something very special here. So when I am doing partial fractions techniques, one, I tried u-substitution and it didn't work, because if that 2x minus 1 dx was in that numerator, well, I would be done. That would be the integral 1 over u, and I can integrate that to the natural log type thing here. But it's not in the problem. And number two, the denominator factors. Now, the technique that we're going to be using is, like I said, partial fractions technique. So what's going on here is this. Just look at the fraction part. 17x minus 2 over x squared minus x minus 12. What we're going to do is we're going to take this fraction and break him up over to its partial fractions. In other words, this is the same thing as 17x minus 2 over x minus 4 times x plus 3. But in the third grade, you learned how to add fractions with a common denominator. Well, we have one big common denominator. We're going to be working this thing in reverse. We're going to be taking the common denominator part and breaking the fractions over its parts. This is part of the common denominator, the factor x minus 4. The other part is x plus 3. Now, these are proper fractions. And what I mean by proper fraction is this. You will notice that the degree of the denominator, which is 2, is bigger than the degree of the numerator. The denominator should always be a bigger degree, and it had to factor. So when you're doing these partial fractions, you always have that idea that the numerator has to be a less degree than the denominator. So when I break this up, this is now a degree 1 little fraction here in the denominator. So the numerator has to be a degree less than that. Well, a degree less than 1 is 0, and a degree 0 polynomial is a constant. I don't know what the constant is, so I'm going to call it a. This one is also a degree 1 polynomial, so the numerator has to be a degree less, which will be 0. It has to be a different constant. I will call him b. So now I'm going to take this fraction right here and break it up into its common denominator partial fractions. That if when I add them together with the common denominator, I'll get back to here. Now here's the whole idea behind what the technique that you're learning here. You're trying to integrate fractions where the denominator factors. And so you got two options. You can either integrate the big fraction, or you can break them up into little bitty fractions. This is a very, very, very important technique that you're going to be using throughout your math career. We use this a lot in differential equations. We use this in many other higher level math classes. So this is kind of a branch off of this. We do it a lot in circuitry, mathematical circuitry for electrical engineering, so forth and so on. There's so many different areas that this is, because here's the basic idea. I can either do stuff on hard stuff, or I can do it on easy stuff. And clearly doing like integral calculus on easy stuff is much easier on the easier fractions. But now the trick is I got to figure out what A and B are. Now I typically teach my students the elimination method because it works the fastest. Let me show you. I want to go find what A and B are. And if you look at this, this is basically, I'm trying to give you guys steps on this, and my step number 3 is exactly that. Go figure out my constants here. All right, so I had this 17x minus 2 over x minus 4 times x plus 3, and that's equal to a over x minus 4 plus b over x plus 3. Now, what I'm going to do to be able to solve for a and b is, first thing I'm going to do is eliminate my fractions by multiplying by the common denominator, x minus 4 times x plus 3. So every term is going to be multiplied by this. This will give me 17x minus 2 equals, because it cancels there. Well, over here I got a over x minus 4 times this. The x minus 4's cancels. You're left with a times x plus 3 plus b. When you multiply b times this term, the x plus 3's cancel. You'll get b times x minus 4. Now again, I teach my students what I call the elimination method. Now this is an equation. I've cleared out my fractions, cleared out my denominators, and so I have a nice little equation here. This equation works for all x. And since it works for all x, and I'm trying to figure out two letters, I can just pick any x's I want to plug into this thing and be able to solve for a and b. I like what we call the annihilators. Now, officially, you can use any x's you want, but I have a brain. So I'm going to use x equals 4, because that would actually annihilate, make 0 for that term. And I would choose x equals negative 3, because it would make 0 for this term, and it makes it very simple to solve for a and b. But when you have x equals 4, plug it into the entire equation. So this is going to be 17 times 4 minus 2. And 17 times 4 minus 2 is 66 equals a times 4 plus 3 is 7 plus b times 4 minus 4, which is 0, which eliminates that term. It makes it easy to solve for a. So a is equal to 66 divided by 7. Now we're going to try to plug in x equals negative 3. So that'll be 17 times negative 3 minus 2. I'm plugging in negative 3 in for x here. I get negative 53. Equals a times negative 3 plus 3 is 0, plus b times negative 3 minus 4 is negative 7. Now, here we go. Again, the goal is to eliminate one of the terms. And then you get negative 53 equals negative 7b, which makes it easy. B equals, when you divide by negative 7, negative divided by negative is a positive. I get b to be equal to 53 over 7. Now, very important, make sure you identify who a and who b is and where they belong. So in other words, this integral that we started with, which the original problem was 17x minus 2 over, it was x squared minus x minus 12 dx, we have broken that integral up into partial fractions. A was 66 over 7 divided by x minus 4, plus b, which is 53 over 7 over x plus 3 dx. Now I've turned one big fraction into two small fractions, but when I integrate, I just got to integrate both of them, and constants go out front. So there'll be 66 over 7 times the integral of 1 over x minus 4 dx plus 53 over 7 times integral of 1 over x plus 3 dx. And like I was mentioning before, it's better to do calculus on easy stuff than it is to do it on hard stuff. This was the original problem here, but you broke it into its partial fractions. Now you can just integrate the small fractions. That'll be 66 over 7. Now officially, I'm doing u-substitution. But remember, the goal is to be able to do this stuff in your head. So if I'm going to do u-substitution, I will let u equal x minus 4. But then derivative of u would be 1 dx. So this turns into 1 over u, which is, when you integrate it, the natural log absolute value of u, and you let u equal to x minus 4. Plus 53 over 7. And again, same type of problem here. I would let u equal to denominator x plus 3. So du is dx, so it becomes 1 over u. And the integral 1 over u is the natural log of the absolute value of u, and u was x plus 3. And then, of course, no bounds on this stuff, plus c. So when you do this stuff on web work, don't forget to type in these absolute values. ABSs is the code for absolute value around this stuff. But this is a very, very important technique that I can't stress how important this is, because you use it a lot in higher level math classes. In the next level class you're going to see this done a lot in will be your differential equations class. But again, circuits class, they use this stuff because they're always dealing with some type of interesting fraction. And when you've got an interesting fraction, if you can break up that interesting fraction, usually applying calculus to it is much, much easier. All right, let's look at some other examples. The next example is this. I want to integrate 2x squared minus 2x minus 9 over x minus 5 dx. Now, this whole chapter is honestly about integrating fractions. But as we mentioned just a few seconds ago, you'll notice that this is not what we call a proper fraction. The degree of the top is bigger than the degree of the bottom. When I'm integrating fractions, I always want those numerators to be a less degree than the denominator. So how am I going to clean this up? Well, I gave you the hint right here. We're going to be using long division. So you got it. Back to old college algebra stuff again. So in the proper technique, I cannot integrate this thing. But what you're going to do is go back many, many moon ago and actually do long division. I'm going to take x minus 5 and divide it into 2x squared minus 2x minus 9 using the long division technique. What times x is 2x squared? Well, that goes 2x. And then you multiply and distribute. 2x times x is 2x squared. 2x times minus 5 is minus 10x. And then when we're doing long division, we would subtract, which changes my signs, and then cancel. The first term should always cancel, and here we go. What is minus 2x plus 10x is 8x. Bring down your next victim, minus 9, and play the game all over again. What times x is 8x? Plus 8. 8 times x is 8x. 8 times minus 5 is minus 40. But then what do you have to do? You have to subtract the old long division stuff, which changes your signs, and get your remainder. The first term cancels. I've got minus 9 plus 40. That is positive 31. Now, how do I rewrite my answer? Well, this is the quotient. Label him Q for quotient, and this guy here is the remainder. And remember, the remainder is a fraction of my answer. So this integral turns into the integral of the quotient 2x plus 8 plus the remainder 31, and you make it a fraction by putting it over what you're dividing by, your divisor, which is x minus 5. So this problem just turned into this problem, which obviously makes it a lot easier to integrate. So this is equal to, and now all you got to do is integrate. This one is the integral of 2x is x squared plus the integral of 8 is 8x plus 31 is a constant. This becomes 1 over x minus 5, the constant hold over, 1 over x minus 5 dx. And again, u-substitution in your head, you would let u equal to x minus 5, which means du equals dx. That would be the integral 1 over u, and the integral 1 over u is the natural log absolute value of u, and u was x minus 5 plus c. And there's my solution. Again, for these 1 over u types, look at the pattern. We're trying to get you guys into doing this math stuff in your head. This is, the more familiar you are with this material, the faster you can get through it. And it's not just about accuracy, but it's also about quickness. We can't sit there and wait forever for you to integrate this stuff. You've got to get this stuff down and looking for patterns on integrations. Basic u-substitution in your head, you don't have to write down. Well, in this section, 6.3, there is one more formula that you're going to need to know how to do. And that is, it's one that you've already got memorized, but we're taking liberties with it and making it into a little bit bigger formula that covers a multitude of different types of problems that you can integrate. So this becomes a new formula. Put it on your list in terms of more formulas you had to memorize. This is the formula for the integral of 1 over u squared plus a squared du. Now if you remember, the integral of 1 over 1 plus x squared dx is the arctangent of x plus c. So this is of the same like. U is your variable, so you got u squared plus a squared. It may not be a 1, it may be some other kind of constant, but that's okay. Then I got a formula. Integral of 1 over u squared plus a squared du is 1 over a, 1 over the constant, times the arctangent or tangent inverse of u over a plus c. So this, again, is a formula, and it's an extension of the arctangent formula that you have memorized, but it covers a whole bunch more different types of problems you can integrate. So here's an example here. Remember, constants on top, they're constants, they go out front. So this becomes 9 times integral of 1 over x squared plus 16 dx. 9 is a constant, it holds over. Now if I compare this formula, you're going to see over here that I want to compare directly. The x squared is the same as the u squared, and the a squared is the same thing as the 16, as I'm comparing. And I have x squared equals u squared, that makes x equal u, and more importantly, when I take dx equals du. So I'm doing this kind of a u substitution because I'm going to plug into this guy. That also tells me a squared equals 16, a is going to be equal to 4. Now officially it's plus or minus 4, but the formula will tell you when you want it to be negative or positive. So just figure out what a is. A is going to be 4. So when I do my substitution, this is an integral, 9 constant holds over. 1 over, this was the u squared plus a squared, and dx gets replaced with du, which you'll notice is exactly the formula. So I plug in my integral form I have memorized. There'll be 9 times 1 over a times the tangent inverse of u over a plus c. So this is 9 times 1 over a is 4. Tangent inverse of u, and u is equal to x over a is 4, plus c, and then all you got to do now is just make it look good. 9 times 9, 1 over 4 is 9/4. Tangent inverse or arctangent of x over 4 plus c. But it's a very simple formula, but you'll notice how to do this, and your teacher will get into this in a greater detail. You really have to use kind of a u substitution technique to be able to match it to the formula so you can make sure you got the constant right and the variable right, because they're going to try to manipulate a lot of this stuff for you guys and also try to set you up for the following section, section 6.4. So one more problem to show you how to do this particular stuff. Now, how can we make it a little bit better for you is do kind of a combination thing here. So this is the integral of 3x cubed plus x minus 5 over x squared plus 9 dx. The first thing you notice is this. I'm trying to integrate a fraction, and it's not proper. What I mean by proper is proper fraction has the degree of the bottom, the denominator, is bigger than the degree of the numerator. Here, the degree of the numerator is bigger than the degree of the denominator. And any time I have that, I've got to do, if the degree of the top is same or equal to the degree of the bottom, you got to use long division. So let's do our long division so we can rewrite this problem. Now, look at this problem. My numerator, which is my dividend, is 3x cubed plus x minus 5. When I'm doing long division, if there's a term missing, you'll notice that there's no x squared in it. When there's a term missing, you're supposed to put 0 in for it. So that would be 3x cubed plus 0x squared plus x minus 5. This way, when you do your long division, everybody lines up. You're dividing it by x squared plus 9. But wait a minute, there's a term missing, so it's x squared plus 0x plus 9. Anytime there's a term missing, put a 0 in for it. Just reminding you from your college algebra days of how to do long division. Now, what times x squared is 3x cubed? You need a 3x. And then you distribute. 3x times x squared is 3x cubed. 3x times 0x is 0x squared. 3 times 0 is 0. X times x is x squared. Notice they're lining up here. And 3x times 9 is 27x. But it's long division. What do I do next? Subtract, which changes all my signs. And you'll notice this term cancels. Also, 0x squared minus 0x squared, well, that's pretty much 0x squared. But then I've got this. I've got 1x minus 27x. That's going to give me a negative 26x, and you bring down your next victim minus 5. And then you play the game all over again. However, x squared does not go into x because this is a smaller degree, so this is called the remainder. So this problem has now turned into the integral. Here's my quotient, which is 3x, plus the remainder, which is negative 26x minus 5 over the divisor x squared plus 9 dx. Okay. You'll notice that when I have this x squared plus 9, it does look like that arctangent formula, but you got to have a constant numerator. I've got two terms in the numerator, so there's one final trick on this one, and that is you keep this common denominator because it doesn't factor or break up or anything because it's a plus, but you can put it under each term. So this becomes the integral of 3x plus negative 26x over x squared plus 9 plus negative 5 over x squared plus 9 dx. I have a single, focused on a single denominator, and I got multiple terms in the numerator. I want to break them up. So this comes into the integral of 3x dx minus, constant goes out front, 26 times integral of x over x squared plus 9 dx minus 5, the integral, pulling my constants out front, and when I pull the minus 5 out front, you got 1 over x squared plus 9 dx. Integrate each part. The integral of 3x, constant holds over 3, integral x to the first is x squared over 2. Minus 26 is a constant, but in here, what technique would I use? Well, this is not a formula I have memorized. It's not the arctangent formula because you need a constant up top. So I'm going to use u-substitution. I would let u equal to 2x plus 9. That makes du equal to 2x dx. Move the constant on the side. 1/2 of du equals an x dx, which is in the problem. So u-substitution is appropriate here. So when I substitute, this becomes integral. This was u on the bottom, and the x dx turns into 1/2 du. And the integral of 1/2 is, excuse me, 1/2, integral 1 over u to u is 1/2 the natural log absolute value of u. And combining it with my minus 26 is going to give me a minus, let's see here, 26 times 1/2, I believe that's like 13. The natural log of the absolute value of u, which is x squared plus 9. So I got this first part. Here comes my second part. And now look at the third part. Minus 5 is a constant. This is the integral of 1 over x squared plus 9. That is of this form right here, of the arctangent form. And so I would let u squared equal to x squared, making u equal to x, and du equal to dx. Also, a squared would be 9, making a equal to 3. So I substitute to show you that I have the formula. This is the integral of 1 over x squared is u squared, 9 is a squared, and dx gets replaced with du. So minus 5 is a constant. Applying my formula, which is 1 over a, tangent inverse of u over a plus c. 1 over a, that'll be 1 over 3. And again, I'm just substituting for this guy, this formula. 1 over a, tangent inverse of u over a plus c. A was 3 and u was x, so that would be 1 over 3 tangent inverse of u, which is x, over a, which is 3. And then we put the big plus c out on the outside. And now I'm going to clean this part up. This will give me minus 5/3 tangent inverse of x over 3 plus c. And this first part was 3x squared over 2. So this is my final answer. And this is a great problem for us calculus professors because it has a little bit of everything. You've got a u-substitution, you got basic integral, and you got your new arctangent formula. Now, majority of the problems that we're going to be covering in this particular section are going to be the ones on the partial fractions, when u-substitution doesn't work and the denominator factors, as it was a proper fraction. The degree of the bottom is bigger than the degree of the top. So your professor is going to show you lots and lots of different techniques of this particular formula, but it's a very, very useful formula that you must get down. I hope this has been helpful, and I'll see you on the next video.